Welcome to the VG tutorials. In this video, you're going to learn how to determine the fiber orientation in a composite material sample in VGSTUDIO MAX. Simulation engineers use the information they get on the orientation tensor from a fiber composite material analysis to validate or fit their process simulations or material models for structural simulations. As here in Digimat's reverse engineering workflow. Take a look at this video for more information on Digimat MX. Now, setting up a fiber composite material analysis in VGSTUDIO MAX can be a challenging task. But no worries, help's on the way. In this video, I will show you how to specify the analysis parameters, how to check if the analysis results are plausible, and how to generate the analysis results in exactly the format simulation engineers need them, to validate their process simulations, or to use them as input data for structural simulations. And this will be our workflow. I will prepare my sample in VGSTUDIO MAX by performing a surface determination, aligning the sample in the scene, and creating a region of interest on which I am going to perform the analysis. Then I will perform the fiber composite material analysis in two different modes. The plane projection mode will allow me to easily verify if the analysis has worked well on my sample and check the analysis results for plausibility. And with the integration mesh mode, I will be able to get the information about the orientation tensor in the right format. Okay, seems like we've got quite some work ahead of us, so let's get started. The sample I'll be working with is a piece of injection molded sheet. The first thing I'm going to do is perform an isovalue-based surface determination. I could perform an advanced surface determination as well, but this would only make sense if my dataset has a very high resolution. Next, I need to take over correctly the sample's coordinate system into VGSTUDIO MAX. For aligning your object, you can use the simple alignment function. Luckily for me, the sample here is already in the right position. Z is the direction of the slab, which is normally the case. And Y is the flow direction. So I can proceed with the next step, which is creating the region of interest on which I will later perform the analysis. The reason why I perform the analysis on a region and not on the entire sample is that I want to avoid distortions caused by boundary effects at cut edges. I'll go to the Select tab and select the Rectangle tool. Then I'll go to the top one window and draw a rectangle. See here. I will leave some space to the cut edge here. Once I have drawn the region in one 2D window, I'll go to another 2D window and extend the ROI into the third dimension. Then I'll create the ROI. And with the ROI created, I can now set up the analysis. I'll select the region, and then I'll select Analysis Fiber Composite Material. On the Settings tab of the analysis, I will now specify the analysis parameters Scale and Integration Area Radius. And then I will use Gradient Threshold to detect the fibers. Let's start with Scale. By default, Scale is set to 1 voxel, and I would recommend that you stick to this default value. You can't go wrong with it. The only exception, if you have a really big dataset and a really high resolution, minimum 4 voxel per fiber, you could do a subsampling by setting this value, for example, to 2, to save memory and computation time. The results will be less precise, but at a really high resolution, there will not be a big difference in the orientation statistics. In my case, I'll leave Scale at 1 voxel and continue with the Integration Area Radius. Here I need to specify the fiber radius, or, in other words, half the fiber diameter. If you know that the radius or the diameter of the fibers, you can enter the value here. I don't, so I'll have to figure it out another way. So what I will do is try and locate some single fibers and get the radius by counting the voxels or measuring the diameter. Let's zoom into the front one window. This fiber here, for example, looks good. Now, to see the voxels, I'll turn off the interpolation mode. And I'm counting 4 voxels, which would mean a fiber radius of 2 voxels. Alternatively, I could measure the diameter of the fiber with the distance measurement tool, and then calculate the radius. Now, some additional info here. With a smaller integration area radius, your result will include more noise. With increasing integration area radius, you'll get smoother results. But neighboring fibers, especially at cross-sections, will influence the orientation and the result will be less local. And if you deal with fiber bundles, which is the case if you're working, for example, with sheet molding compound or woven fabrics, you can increase the integration area radius to the radius of the entire fiber bundle. Okay, back to our sample. I will enter half of the diameter I measured with the distance tool, and with that, I have specified the integration area radius. Next, I need to detect the fibers, and I will use the gradient threshold for that. First, I'll turn on the preview. And then I'll raise the value for the gradient threshold until all the fibers are correctly detected in the preview. Don't worry about over-segmenting here. In this case, it's better to segment too much than to leave too many fibers undetected. Okay, all that's left to do is select the mode in which I want to run the analysis. A quick info here. No matter what mode you select, once specified, the analysis parameters will always stay the same. For the first run, I will select Plane Projection mode. This mode requires an analysis direction. In our case, this is the Z direction, which is the top one window. And that's it. I have set up the analysis, and I can click Calculate to start the analysis. And here we can already see the color-coded analysis results in 2D. For my taste, the colors are a little too shiny. So let's quickly go to the Colors tab in the Analysis dialog and make them a little more transparent. Much better. Now let's close this dialog here and take a closer look at the analysis results. With the Plane Projection mode, I can see the local orientation of the fibers very nicely, which allows me to easily check if the analysis has worked out fine and the orientation of the fibers has been detected correctly. What I'll do is I'll compare the orientation of the fibers here with the orientation of the colors in the color disk, the green-colored fibers with the green color in the color disk, the yellow-colored fibers with the yellow color, the magenta-colored fibers with the magenta color, and so on. I think you get the idea. And, as you can see, the orientation of the colors match pretty well. And if they match well, it is a good sign that you have set up your analysis correctly. Well done. What you can also do in the Plane Projection mode is take a look at the orientation tensor plot. You'll find the plot in the Analysis dialog, just double-clicking the analysis. The orientation tensor represents a fiber orientation distribution. There are 6 components of the orientation tensor. The plot shows a graph for each of these components. We're not interested in the fiber volume fraction for now, so let's switch that off. Simplified one can say that a high value in, for example, XX, means that a high fiber fraction is oriented in X direction. And the same applies to YY and ZZ. For injection molded parts, the ZZ component is usually lower than 0.1, Z being the direction of the slab. What I can do now is take the pole and move it along the plot. For example, at this position here, the YY component has a value of 0.8. Since the sum of the tensor components together will always be 1, 0.8 means that at this position, a high fiber fraction is oriented in Y direction. Now, the scene always shows the slice corresponding to the current position of the pole. And when I take a look at the Z view, that is, the top one window, I can see that the orientation of the fibers is indeed in Y direction, which means that orientation tensor and slice match pretty well. In the case of my sample of an injection molded sheet, I can see the characteristic regions over the thickness in an injection molded part when moving the pole along the plot. In my sample here, Y is the flow direction. On the edge, the fibers, due to the flow conditions, are aligned in flow direction. While I am moving the pole towards the core, this changes slowly. Until, in the core of the material, due to a change in the flow conditions, the fibers end up being aligned perpendicularly to the flow direction. And when I continue moving the pole towards the other edge of the sample, the fibers are again aligned in flow direction. Plot and slices match well. So, this is another way to verify that I have set up the analysis correctly, and that my analysis results are plausible. It may seem a little bit complicated at first sight, but what I would recommend is that you just give it a try. Take a closer look at the orientation tensor plot, move the pole along the plot, and take a look at the tensor components and the corresponding slices in the scene, and observe how the orientation changes. With a little bit of practice, you will quickly get the hang of it and be able to confidently judge if the analysis results make sense or not. Okay, we've seen how to set up an analysis in plane projection mode to check the results for plausibility. As a next step, I want to generate the analysis results so that they can be used for validating process simulations or as input data for structural simulations. To do so, I'll perform the analysis again, using the same analysis parameters that I have specified before, but this time, I'll use the integration mesh mode. First, I'll copy the analysis and double-click to open it. As you can see, the analysis parameters are the ones we have already specified. All I have to do is change mode to integration mesh and create the integration mesh. I want to create an integration mesh with 11 cells alongside the sample, so I'll select one cell for X and Y respectively, and 11 for Z. I'll click Apply and Close. And then I'll start the calculation. Once the calculation has been completed, I'll go to the Mesh Cells table. This table gives me the information on the orientation tensors in the respective cell in exactly the format the simulation engineers need the data for their simulation programs. I can export the table by right-clicking and selecting Export as CSV. And that's it. Now, you may have noticed that the fiber composite material analysis in VGSTUDIO MAX offers a variety of analysis modes. If you want to know what mode to use for what class of fiber composite material or manufacturing process, check out the information on our website under Products. Add-on modules, Fiber Composite Material Analysis. And you'll find a detailed tutorial on the fiber composite material analysis, as well as other material on our documentation landing page via Help, Show Tutorials. Plus, make sure to register on Nexus and make it your go-to place for sharpening your expertise. Get access to this video and other information material to get the best out of our software. And visit the VG community to exchange ideas, ask questions, and discuss topics with other users and our Hexagon experts. And stay up to date on the latest news and developments. Register now, a world of insight awaits. Thanks for watching, and see you soon on Nexus.